All right, in this chapter, we're going to cover two things. The first thing we're going to look at is linear approximations, and then the second thing we're going to look at is differentials. And you can see how one sort of leads into the other. Linear approximations gives us a good idea of exactly how differentials work. So if it seems kind of arbitrary that we're doing them both together like that, the reason is that one sort of feeds over into the other. So first, let's look at linear approximations. So linear. All right, so your idea of, focus. Okay, so the idea of a linear approximation is, let's say you have some graph right here. All right, and we'll just sort of give it maybe a curve like that. And let's say you have some point right here on this curve. All right, so we're going to call this A, and F, whoops, and F of A. Sorry for that little. All right, so now what a linear approximation says is, well, if we take the rate of change, the instantaneous rate of change, or the derivative, right at point A, then we can approximate some other point on the line. We'll call it X. X will be right there. We can approximate X by saying, well, we're going to take the function at A, and then we're going to multiply this slope by the difference of A. So this point right here, this can be approximated by, we have our first one, F of A right there, and then we're going to go right along this curve. So we're going to have, well, not the curve, on the straight line. So F prime at A times X minus A. So, and then X minus A is just this distance right here. So, you know, and you can see, especially if as X minus A gets really small, this can be really helpful. Now, if X minus A was really large, you can still get an approximate in there. Let's make this X a little better. There we go. You can still get an approximate in there, but it's not, your error is going to be a little bit more than you might really like. So let's take a look at it here real fast. So let's say we have something easy. We'll say x squared. So zoom out here. All right, so there's x squared. And then the derivative of x squared, that's going to be 2x. And then let's let it, whoops, y isn't that typing? Y equals 2x, and then let's have it intercept at 1 right there. All right, so here's where it hits. So you can see if we bring this in real small, and let's say you wanted to estimate like from 1 to 0.01. You know, pretty much that's going to be on the same line. But the further you get out, you can see, keep going back. You can see that like at 1.1, we're a little off, 1.15, we're further and further off. So this is the idea of linear approximations, is we can use the rate of change kind of as a quick way to make some sort of an approximation, but it's, keep in mind, it is going to have a little bit of an error in it. So this leads us into the idea of differentials. And again, you might be sort of wondering like, wow, this seems kind of weird, you know, because we already know how fast the actual function is changing. So why would we necessarily have to use this idea of differentials? And the reason that we would is they can tell us some really useful things about how y changes with various changes in x. So let's take a look. The way that they write it out in the book is that we can see differentials. Okay, so with differentials, we have some change in y is going to equal f of x plus some change in x minus f of x. And if we look up here, all that we're going to be looking for with this change in y is how much, if we just use our example up here, how much is y changing with changes of x. So so this can be approximated. Now we'll approximate it as dy equals f prime at x dx. And you see, if you divide both sides by dx, you get dy dx equals the derivative of x. So that's that's, you can kind of see how we get a lot of that stuff. So so again, you might be like, wow, great, that doesn't that doesn't seem to buy me a whole lot. But let's take a look at an example, and maybe with an example it'll make sense a little bit. So let's say that you have a sphere. Okay, so here's your sphere. Oh, here, let's put example. Okay, so you have a sphere. There we go. And there it is, and then we can draw the little line around it like that so that we know. Okay, my drawings are not the best. Okay, so let's say that the radius of this sphere equals 4. Okay, so the question you might want to ask yourself, here's your question. How much does the volume change, so total volume change, if we increase the radius by 0.001? Let's just call this inches. All right. Oops. Question mark. Okay, so that's our question. I'm going to scroll this down here. Well, let's see how we would use differentials to answer this. So I know that my original equation, we'll just call it, I'm going to use y and x because that's going to help it sort of c relate to here, although you'd probably use r, v and r really, but all right, so I'm going to use y and x. So y is going to equal the volume equation. So 4/3 pi r, wouldn't be r, it'd be x cubed. All right, well, let's take the derivative of this. All right, so if I take the derivative, f prime, well, 4/3 times pi just is a constant. So really we just have the derivative of x cubed. So that equals 3. Well, oops, sorry, I'm getting ahead of myself. So that's just going to, sorry, that's my erasing marks. So that's just going to be 4/3 times pi times 3x squared. All right, so let's simplify. 3's are going to cancel out. So I'm left with 4 pi times x squared. Okay, so that is going to be the derivative. So now I know that my change in y can be approximated by that derivative times how much I'm going to have x change. Okay, well, I've already figured out all of this. So my derivative at x, and x is going to be 4, because that's where we're starting from. So that's going to be 4 thirds, 4 times pi times, since we're at 4 squared, so that's 16. So I've got 4 times pi times 16, then times the change in x. So that's going to be 0.001. So we get out our calculator, voila. And it's pretty easy from here. I've got 4 times pi times 16 times 0.001. So that equals 0.20 cubic inches. So I know that for every 0.001 increase in the radius, that's going to result in a 0.20 approximately increase in the volume. So you can see how this would be helpful. Like, let's say that you're designing these spheres and you want to have your tolerance within this, plus or minus this. Well, then you could use these differentials to figure out, well, what's going to be the max and min volumes that you're going to have. So when you're looking at any time that something changes, like if you want to add a certain amount or take away a smaller amount to a certain thing, then differentials are going to be really helpful for us to be able to quickly estimate exactly what that's going to be.